Good. Segment 1 bit. Okay, let's center this all. Well, this part we don't have to, but this we do. 1 bit. Centered, not a crossover region. All right, let's center it. Who cares? Fine. Okay, so that's the version I think you were asking me about. But when I wrote the example, I did it this way. Both are valid. I didn't create this. In the literature, you could do it one way or the other. I just didn't remember that I did it that way when I did your sample. So that I apologize for wasting your time. But it was interesting. We now showed another aspect of practical implementation. This really is. I didn't make this on the fly. So, okay, that's the segmented crossover. Any questions? I believe... Oh, the 2 more. Oh, the 3 more. Okay. Well, let's be for completion's sake. All right. There's uniform crossover, shuffle crossover, although shuffle can be used with everything. Shuffle is just a auxiliary technique, an interesting one, but auxiliary. And cut and splice, it relates to the discussion I just had with Walid, but because it's so unique and not very often done, I'm going to leave it at the end. Uniform is the more typical one. Which is the version that, I was about to say the version Goldberg did. Give me a second. I have to remind myself. He may have done 1 point. I have to remember. I don't remember. He either did 1 point to uniform. When we get closer to the schema theorem, I'll say it. So I better not make that point now. Anyway, uniform crossover, let me just say, dovetails if you notice the progression of growth, uniform crossover dovetails, as it were, follows directly, dovetails the endpoint of the segmented crossover. But here, each point, I hate to say toggle. The point is that each point is its own region. So you don't toggle. It's not before or after. It's the point itself, and then the probability P with so uniform crossover is where, in essence, it's similar to segment endpoint with probability P. Similar to n equal chromosome length with probability P, and you'll see how. So it takes some of the elements of the last few. It takes a bunch of different elements of the last few versions. Well, I don't know. So but here, this is an important distinction. It's not so effectively. There's no toggling. Anyway, enough discussing the philosophy. And one example will make life simple, and you'll understand it. We'll do in 2 seconds. N equal 2 for B. Help me out. N equal 2 for B. Oh, that's interesting. Yeah. So Mohammed, I got it. Correct. So Mohammed, this is a little bit of a problem in the literature, which I point out somewhere in the notes. That I'll email you, I think, of the example. While in this example you're correct, ultimately you don't want to view it that way. So be careful. See, that I was purposely dancing around this very given point above. I don't know if you got it. Well, I did equal to 2 crossover, 2 point crossover, I was dancing about it, right? Because I said that, what do? I said that the region is between B4 and B6. But if I sort of, maybe under my breath, but I didn't mention it. Really, because if you know 7677 doesn't say that. 7677 says you toggle. It turns out that B4, B6 is the region. But that's not the philosophy. In order to be consistent between N crossover and 2 point crossover, so we can't really talk about 2 point crossover as bracketing a region, although it's easier to relate to it by saying that, because that's not philosophically what's happening. What's happening is you only toggle twice, and that's the 2. It's not that your 2 points define a line in between them, like Euclidean, but rather it's that you only toggled twice. In this example on your board, you toggled after B3, and then you toggled back after B6. Net result is you have one region. But philosophically, that's not what happens. Philosophically, two-point crossover is identical to n-point crossover, just that n equals 2. So so you got to be careful about the philosophically what's going on. Delete anything here. Let's see if I too many spaces. So be careful about the philosophy. That's all I'm saying. Anyway, let's do an example for uniform. Uniform is where n equals every possible point, but the major difference here is it's not after, it's on the bit. Okay, not after the bit, but on the bit. As I say, one example clarifies very quickly. All right, let me get an example. Oh, so, wow. Oh, wow. Ah. Wow, is that interesting? Give me 1 second. Yeah, very interesting. I don't know. By accident, I copied over notes. Okay, fine. That's no big deal. All right. Let's do this example. Right here. All right. In uniform crossover, which is recommended in your own GAs, okay, we can use the same example. Okay, so note. All right, hold on a second. Let me make some comments, and then we'll put this example up. 1 or 2 comments. Uniform crossover is a favored version used by researchers in practical GA. So that the people like this. Okay? Okay. The probability rate gets, in this case, now gets a sort of a unique name. It's not a very unique name, but just that it's called the following. In this context is now called, although in this context is now called and it's no really fancy name, but it's called the crossover rate as opposed to the probability rate. Okay? But when you talk about uniform crossover, the rate isn't usually called the probability rate. Technically it is, but that's too generic. Now in this context, it's called the crossover rate. Okay? All right, so assume that the crossover rate is equal to 3, just so that we'll compare and contrast the results between this and segmented, that the crossover rate equals 0.3 or 30%. It's equal to, okay? It's equal to 30%, whatever you want to do it. Okay? As mentioned above, there are 2 ways to implement this. And in this example, we're going to do less than or equal. The associated random number generated is less than or equal to the crossover rate, which I should say in this context is the standard way researchers do it. They're equivalent, and there's nothing better one way or the other, but I just want to point out that if you actually look at code, that's the way they have to like it in this context, which in this context is the favored implementation by researchers. Okay, now, one more note, which we've mentioned above, which is, please note again, that these numbers are only used once. Well, I don't mean they can't happen to quote-unquote appear only once. These numbers are used for this example only, are used for this example. But if need to perform uniform crossover again, you will need to generate a new set of random numbers. Be associated with each bit. Be associated with each bit. Beautiful. Okay, so let me edit that 1 second. New set of random numbers associated with each bit. Beautiful. Okay, so let's now go through our example. In this case, okay, we got to get rid of these lines here. Format cells. Sorry. Good. It's cleaned up. So let's get started. 0.5, no. 0.4, no. I'm sorry, I'm tired. 0.7, no. 0.29, yes. 0.86, no. 0.9, no. 0.01, yes. 0.11, yes. So let's say it that way. No, yes, no. Because bit by bit, each region is 1 bit. No. Yes, crossover. Oops, sorry. So the right way to think about this is not the crossover, this is just the layout. The right way to think about this is as follows. Like this. There you go. All right, now we're going to, based on this, show what the result will be. So I'm just trying to center this. Hopefully it looks a little nicer. Okay, now, so let's now say the result. Okay, what's the result? Give me 1 second. Okay, I'm deleted. Oops, nothing there. Sorry, there was a researcher and he doesn't realize I'm teaching. I don't know what happened. All right, lost that. Give me 2 seconds, sorry. Okay, we're good. All right, I don't know what happened. Okay, the result is as follows. So no, yes. Okay, so then this is going to become like this. So the 0 from bit string 2 now goes into bit string 1, and the 1 from bit string 1 goes to bit string 2. No is the same. So now we have this yes. So that the 0 from bit string 1 goes to bit string 2, and the 1 from bit string 2 goes to bit string 1. And then finally, the last one, the 1, 0, and 8, the 0 goes to bit string 1 and B8, and then finally the 1 goes into B8 to bit string 2, and these are the resultant children. Okay. That's the example. Oh, I'm sorry. Okay, yeah, it is the most popular. I've asked the bottom lines are going to be, as they say colloquially, the proof is in the pudding, right? You look at a chocolate pudding and it looks delicious, and then you want to know, is it delicious? Well, you can conjecture by the way it looks that it looks delicious. It's only when you taste the pudding. The proof is in the pudding, right? What's the proof? The proof will be when you get it. A good result for my GA. Yeah, I like uniform. You are right. So it's intuition by GA is more of a philosophical concept. But the fact is, you'll do whichever version gets you the better answer, right? I think so. I think you're in the end going to do whatever gets you the better answer. So it's a little bit contrived, unfortunately. It's genetic algorithms. It's a little bit contrived. You won't do what seems better for genetic algorithms. You'll do what does better, because it's result oriented in the case of genetic algorithms. All right. Anyway, all right. That's the answer. Good. So, any questions about uniforms? Once you have the example, it's very easy to see what's happening there. Okay. All right. There's one last. Well, okay. There are two. Two others, and then we're done. I'm sorry. A question, Professor. How do crossovers go from parent to child? Yes, they do. Bitstring 1. Okay, I don't say it here, but I mentioned it above. Bitstring 1 is parent 1, and bitstring 2 is parent 2. Okay, does that help you, Mohammed? Yeah, no problem. Good. But what did I just do? Okay, let me just make sure it's still there. Yes, it is. Good. All right, let me save this. Okay, so now the next version, there are two versions left. The first version is sort of an auxiliary version in that you could use it with any other version. But it's an interesting thing to mention. Shuffle crossover. So shuffle crossover, as I say, people, so, literature, how did they implement it? Let's see if I wrote it down. I don't even remember anymore. I don't know. I guess I couldn't find it. All right, but here's the idea: shuffle crossover. Shuffle crossover is afraid. What gave rise to shuffle crossover? Okay, so first, note that first, shuffle crossover is more of an auxiliary technique than a independent crossover, in that you have to do the shuffle in conjunction with one of the other above crossovers. Okay, so we'll pick one. For simplicity, just very simplicity, we'll do 1 point crossover. Right, it's the most simple version. That's the first point. Okay, good. All right, that's the main point. Okay. Now, so what is shuffle crossover? So let's take our original bit string. All right. Okay. Now, the second point is, what is it dealing with? Okay, I'm sorry. Yeah, I want to say why did anyone come up with this? Truth be told, that if your random number generator were of such high quality there would be no need for shuffling. And you would use one of the above techniques alone. Use one of the above techniques by itself, or as is. Okay. So the issue at hand is the following. The problem is that they assume is when you're generating your random numbers or to get these selected points, there's a possibility that your random number generator is not that good, and that there's some sort of dependency between, usually there is, between one number generated and the next number generated, right? So if the quality, let's make one more line, if the quality of the random number generator is not so good, so generally there will be a dependency created between two consecutive numbers generated by that algorithm. So two consecutive numbers produced by that generator. Okay? To mix things up, like the annealing, using that word again, that's the idea. To mix things up, to make things more random, locally mix things up, Shuffling will change this. That's the background. So let's give you an example, and then you'll understand. All right, here we are. Now, what you do is randomly create a permutation of the numbers 1 through 8. Or 1 dot dot, using our naming, chromosome length, here 8. Chromosome length, which here equal to 8. Okay, so I'm going to ask you to participate in this process. Randomly text a number from 1 to 8, and whoever's texting next, make sure not to text a number that's already texted. So somebody start. Okay, number 5. Don't use 5. Someone else. 5, 6, 8, 7. Continue. So now we're 4. 3, 1, 2, 4. 1, 2, and 4 left. Somebody, 2 or 4? Somebody? 4, and hence the last numbers. Stop. Okay, Bola and Frederick got it. Good. So that's exactly great. You did it. Beautiful. So you shuffled, which means permuted. If we didn't get that, shuffled means permuted. Okay, so in our example, we have what numbers? 5. So B5, and then you had 6, 8, 7. And then we had B3, 1, 4, 2. Okay, so now, doing the permutation, what you get is the following result. So let's copy B5. Oh, I'm sorry, this no, yes, no, that's not relevant here. That's only for a uniform. So we copied B5. Let's now copy B6. Let's copy B8. Copy B7. Let's copy B3. Copy B1. Let's copy what's B4. And finally, let's copy B2. Okay, and let's clean this up a bit. First of all, let's do it by making a box everywhere. Let's do it this way. Oh, no, this way, right. Okay, so that cleaned that up, but we need to renumber it because it's no longer, these are the source bit numbers. And these are the shuffled bit numbers or new bit number. Okay, so it's B1 prime. I can use small. That's not bad. Let's use small. B2, B3, B4. Right, just to differentiate the two. That's not bad. B6, B7, B8. I was going to use prime, but that's not bad. Okay? So these are the source bits. These came from 5 through 2, and they're now B1 through B8. Okay? Small b being a different sequencing convention. All right, now we're assuming for simplicity, we are assuming 1 point crossover. Assuming 1 point crossover. Okay, so could someone randomly give me a crossover point? Again, it means that the crossover occurs after that. So somebody could give me a one bit. Which bit should I cross over? Somebody randomly give me. Somebody pick a number. Okay, Pima 1, Justin. So after 3. Fine. Okay, so it's after B3, right? Just to be consistent with our notation. That it's the b's, small b's is the new ones. Okay, so the result is going to be the following. All right, so the result is the following. All right, so we said after B3. So let's change that. Okay. Well, I'll leave that as is, but here it's easier the other way. 1 second. Let's get rid of the lines. All right. Okay, good. So the line is here after B3. Good. Okay, well, that's not the result. So that's the crossover. And now the result will be the following. result will be the following. So what's the result? So one more time, it's after B3. So I guess we do that like this. So up, and then this moves down. Right? So that's the result after using the crossover of small b3, right? But now we have to put it back in the original form. But now reshuffle back, inverse permutation, reshuffle, inverse permutation, back to original form. Okay, and let's do that. Give me 1 second. So this takes a little bit of time. Oh, actually, you know what? Okay. Give me a second. What's the easiest way to do this? Okay, I think let me put the sign first and let's continue. Okay, so who's the B1? That's the big B1. So let's copy this here. And then, oops, I meant to copy, not cut and paste. Copy B1, copy B2, copy B3, copy B4, copy B5, copy B6, copy B7, and then finally copy B8. Okay, let me clean up the format. Let's hope. Oh, no, I don't want that. Well, for now, that may make things easier. Let me do it this way. Let's get rid of this line. Okay, actually, we need the entire. Now it's just back to the original. So everything is like it was originally. And then finally, we want the color to be the same. Let me just change that. This is yellow, and this is all orange. I didn't want red, although that's interesting. But I didn't want to do that. Okay, very good. All right. Before I read any comments, you know what? Let me get the text joined so we see what the actual strings are. Good. And let's call this, well, more than just a result, this child 1, this child 2. Beautiful. Okay, so that is shuffle diplomacy, shuffle crossover. Oh yeah. Okay, here comes the question: Do we do all these to simulate natural mutations? So interesting question. In the literature, none of this is called mutation. Don't get me wrong. Your question is better than the answer. I agree with you, and I alluded to this when we first started today. The illusion was I made a small comment, but you're really asking a good question. It came to the point where you don't recognize this as being crossover as much as you are seeing that we're purposely changing things sort of randomly, which sounds more like a mutation, right? In essence, that's your question. So you are right. To the outside lay person who just, it's the person who's not trained in GA, if they were to observe what you're doing, they would have called this all mutation, and I agree. The fact is the literature doesn't, and being GA people, we have to call it crossover. So although I totally agree with you that some of these far-fetched versions do sound more like mutation than they do crossover, I agree. In the literature, they will never allow you to say that. So we're stuck. These are all called crossovers. And in a second, we will do mutation. Fortunately, for classic mutation, there's only one version, so we're lucky. And that version is based on, in classic mutation, it's based on uniform. So things are a little simpler in a moment. Anyway, but excellent question. Does that address your concern, Mohammed? Good. Excellent. Good point. Very good point. Okay, now. Okay, the last one is more of a curiosity, although you could probably see why it's been done. In GA less so, I will admit in genetic programming more so. In fact, in genetic programming, the version using trees is really cut and splice. And maybe that's why people said, let's have it for GA also. but it's not so normal. It's not so typical, and it's not something that you really like to do.